Today we're going to go through some more stuff on the mole concept and see how we did here on the stuff that we covered the other day. First one here was to figure out the number of grams and 13.3 moles of lithium nitrate. Correct answer here, good. 917. 917. Now, to set this one up, of course, we are given what in this problem? We're not given mass. What are we given? Moles. So we're given 13.3 moles of the lithium nitrate. And what is it we're looking for in this one? Grams of lithium nitrate. We then need a conversion. On the top we would put in grams of lithium nitrate, on the bottom moles. And what number is going to go on the bottom? 1. And on top would put in 68.95. Okay. Now these are going to cancel out. Where does the 68.95 come from? From the periodic table. We'd sum together the masses of 1 lithium, 1 nitrogen, and 3 oxygens. Any questions on this one? All right, next one. We'd like to know the number of moles in 13.3 grams of lithium nitrate. The correct answer on this one is 0.193. And of course that would be in units of moles. So the only difference between the first one and this one, in the second one we are given 13.3 grams of lithium nitrate. And what are we looking for in this one? Moles. And so we take the conversion from the first one, and what do we do with it? Flip it over. So we have 1 mole of lithium nitrate for every 68.95 grams of lithium nitrate. Of course, these cancel out, and then we get the answer of the 0.193. If we go on to the next one, we have a helium-filled balloon that contains 3.0 times 10 to the 23rd atoms of helium. This here would be the same as. And the correct answer, let's see, there's a few of them. Looks like there's probably as many or more wrong answers than right answers. The correct answer is 2.00. Correct answer is 2.00. So this one we probably better go through for sure. Let's go ahead and start this one off. What is it we're given in this problem? Atoms. How many atoms? 3.01 times 10. Remember, you always start off with what we're given. So in this case, we're given the number of atoms of helium. What is it we're looking for in this problem? Grams of helium. So now if we write down our conversions, we kind of showed how we made this list the other day. For every 1 mole of helium, how many grams do we have? Right here, yep, 4.003 grams of the helium. So 4.003 grams of helium. And this amount contains how many atoms? 6.022 times 10 to the 23rd atoms of helium. So now that we have this relationship, this is our 3-way relationship here. We don't need all of these components, but we do need 2 of them. Which 2 do we need?
We need grams and
we need grams and atoms. So we need these 2 right here. We then place them into the problem. On the bottom we'd put in 6.022 times 10 to the 23rd atoms of helium. On the top we'd put in 4.003 grams of helium. Atoms of helium are going to cancel out. And if we want to make this easy, what else will cancel out?
the times 10 to the 23rd.
10 to the 23rd will also cancel out. So we take 3.01, we divide it by 6.022, and multiply it by 4.003. And when we do this, we round off our answer to 3 significant figures. That would be 2.00 grams of helium. Any questions on this one here?
So we just have to remember that in each, like, periodic table gram, that's how many atoms the Avogadro's need.
Right. If we're talking about elements, it's that number of atoms. It's Avogadro's number of atoms to that element. So in this case, it's 1 mole of helium, 4.003 grams of helium, and Avogadro's number of atoms of helium. And remember, Avogadro's number is a huge, huge number. We talked about that the other day. And a huge, huge number is always going to go with what type of unit? A super, super, super tiny unit. If you're applying it to grams, like if you would ever put this number in front of grams, you're probably talking about something that's close to the mass of the Earth. Okay? So we'll only ever apply such a huge number to something really tiny like atoms, molecules, or formula units. Okay, then I think we had one more. And the next question was, and now we didn't cover this yesterday. This is our introduction for today. So I wanted to see how we did with this one. I don't think that I marked this one right or wrong. It says between NH3 and NH4NO3, which substance would you predict supplies the greatest percentage of nitrogen by mass? Looks like we have about 28% of us on NH3, 69% of us on the NH4NO3, and then some of you willingly admit you have no idea, and that's fine. So now let's talk about what these substances are, and this is going to be the basis of our calculation here today. Right here. Now you should know one of these two already. You should know the name of this one. What is the name of this substance right here?
Nitrate.
It's nitrate. What type of nitrate?
An ion, or
What is it?
ammonium.
Ammonium nitrate. Good. This is ammonium nitrate. And ammonium nitrate is comprised of ammonium ions and nitrate ions. Now some of you might decide that you want to try to name this one. If you do, you might try naming it as nitrogen trihydride. We don't name it that way. Just like if you see this formula, H2O, we don't call this one dihydrogen monoxide, even though that would be a correct name. We call this one water. So likewise, when we see this one as a formula, we don't name it by its, I guess, its systematic name. We give this one its common name. Anybody know what NH3 is? This is one that from this point forward, you must know it. This is ammonia. Not the ammonium ion, this is ammonia. And this is a neutral compound. Now the two aren't to be confused with each other. Even though you can make ammonia out of ammonium compounds, and you can make ammonium compounds out of ammonia. But again, they're different things. So NH3 is ammonia, and from this point forward, it is expected that you know when you encounter it, we wouldn't call it nitrogen trihydride. You're going to refer to this as ammonia. So now, these two are very different substances. In fact, I brought up some pictures of these today. I think I've told you before that I was raised out in the country, kind of a hobby farm type thing. And so I know a lot about this stuff. But as far as how these forms come in, this is one of the ways that we find ammonia. So if you were to go driving out in the country, you're going to see these big tanks out there of anhydrous ammonia. The word anhydrous, we analyze what this stands for. Hydrous, what does that sound like it might contain?
Hydrogen.
Water. But if it's anhydrous, that means it doesn't contain water. So basically this is ammonia that doesn't contain water. So this is what might be considered dry ammonia. And ammonia, actually, if you were to use some household cleaning products, when you use ammonia products, you'll smell the ammonia. What you're actually smelling is molecules of NH3. And That's all that's contained in here, and ammonia is a gas. So what's done when farmers apply this is that they apply it as a gas. In here, though, it's actually liquid. It's compressed down so that gas turns into liquid, and then they will be able to apply it on the fields. They'll pull this through, and the one kind of neat thing about ammonia is it's super, super soluble in water. And so one of the distinctions here is when we talk about it being anhydrous, it's important to a farmer that it is anhydrous or dry because it's very much water seeking. If it's contaminated with water, that ammonia is already going to dissolve in that water. So they want something that's totally dry, so when they put it out in their fields, any moisture that's in the field, this stuff would wind up dissolving into. Now there's another show that if you happen to have watched this show over the years, would have seen a fair amount of this. In fact, out in the country, these things are often stolen. Any idea what these are used for?
Bombs.
Not bombs. Drugs. You know which drug?
Meth.
Meth. Yep, methamphetamine. So this is often used in making meth. And so it used to be that these used to just set out in the fields wide open and everything. Now they have to be under a lot more security than they once do because we've found sophisticated ways to steal things and whatever else, and we need to kind of keep those under lock and key. This one over here, this is the ammonium nitrate. This is NH4NO3. This is also used as a fertilizer. Now this is probably the fertilizer that you're more familiar with. If you buy, go to a store, say like Menards or Home Depot or a gardening store, you're going to see big bags of fertilizer. When this is placed out in your lawns, you go ahead and broadcast it out and everything, and then it sits on top, and as it rains, then it dissolves and goes into your soil. Now you actually don't buy ammonium nitrate. If you buy a product, you might buy something like urea or ammonium phosphate or mixtures of things that this would be found in. But this too has its dangers. In fact, if we go back to dangers, because this is so soluble in water, it takes a special license to handle it. Farmers have to get trained to use this these days. They don't just let anybody use it. But if it's super, super soluble in water, your body is comprised of about 2/3 water, okay? And your mouth, obviously you have water there, your eyes, your mucous membranes and everything. So if this stuff gets out there and it wants to dissolve in there right away, this is a base and it causes burns. And so if you ever notice, even when you're working with a household cleaner that contains ammonia, that's probably only 1% ammonia. When we increase that concentration to 100% ammonia, that stuff can cause burns very quickly. And so when there's ever an ammonia leak or whatever, you'll probably hear that they evacuate entire areas because this will wind up being super irritating if you wind up being exposed to this because of the fact. In fact, people have died by being exposed to it because it dissolves so rapidly into the water that might be exposed, like your saliva or mucous membranes, eyes, whatever, that it does require the special handling. But that's why it's effective when farmers put this in. They often put it in the fall, and so they can go through there, inject it in the soil, and of course there'll be some moisture in the soil, and that moisture will retain that ammonia until spring comes around. This stuff here, the ammonium nitrate, this also requires special handling. And I realized last semester now that many of you are too young to even remember this, but there was an event that occurred back in 1994 in the city of Oklahoma City, where the federal building in downtown Oklahoma City was bombed, and there was about 180 people that were killed. That was considered to be an act of domestic terrorism. But what somebody had done is that they had filled up a rental truck full of ammonium nitrate and then doused it with diesel fuel and then ignited that, and it put a crater in the road of about 15 feet deep. Okay, so this stuff here is also stuff that, like I say, they don't sell to the ordinary person. You need to get trained or whatever else with this today, and it's very highly controlled. But each one of these, if we go back and look at the formulas for them, what do you suppose it is in each one of these that we're interested in getting into the soil? We're interested in getting in the nitrogen into the soil. Okay, so these are used to get nitrogen in. So now, when a farmer makes a decision as to what to put in, again, one might be the solubility or the time of year, but another consideration might be the percentage of nitrogen by mass that's in there. So what we're going to do here today is we're going to calculate that percentage. This is one such application. And if we calculate a percentage, percentages are always, it's not just in chemistry, percentages are always calculated this way. And how do we always calculate a percentage? Part over the whole. Then what? Times 100. Okay? So percentages are always the part over the whole times 100. So if we want to find the percentage of nitrogen, let's start first of all with the ammonia over here. How many nitrogen atoms are in ammonia? How many nitrogens? 1. How many hydrogens? 3. So what we're going to do now is we're going to calculate that molar mass. So we have 1 nitrogen coming back to the periodic table. 1 nitrogen at 14.01, 3 hydrogens at 1.008, 1 at 14.01, 3 of them here at 1.008. We then multiply these through, we get 14.01. This is going to be 3.024. If we then sum down, we'll wind up with 17.03. And of course now this is going to represent the number of grams of NH3 contained in 1 mole of NH3. So from here, if we want to find the percentage of nitrogen that's contained in there, percentage of nitrogen, we want to take the part that is nitrogen. And what is the part that is nitrogen? 14.01. And by the way, this is going to be the grams of nitrogen. This is going to be the grams of hydrogen that's contained in the ammonia. So we'll take the 14.01 grams. We'll divide it by the whole, which is 17.03 grams. Of course, grams over grams are going to cancel. We'll multiply that result by 100. So again, 14.01 divided by 17.03 times 100. And now, I guess this would be 4 significant figures. This is going to be 82.27. And then we'll label it as percent nitrogen in ammonia. So let's go over, and you do the next one here. Find the percentage of nitrogen in the ammonium nitrate. Find the percentage of nitrogen in ammonium nitrate. And once you get your answer, you can check it out on the Socrative app. If you don't see one of your choices on the Socrative app, that means you've done something wrong, because one of the choices is up there. Give me about 1 more minute. Okay, we've got about 30 seconds. Okay, we'll take about 10 more. Get our answers locked in. We'll count down. 5, 4, 3, 2, 1. Hey, how about that? I like that. All right. Wonderful. Great job. And so setup would look something like this. So now if we went back and had to re-answer our question, between ammonia and ammonium nitrate, which substance supplies the greatest percentage of nitrogen by mass? The correct answer is going to be?
Ammonia.
Ammonia. Exactly. Ammonia. And that's why you'll see most farmers will actually choose the application of ammonia rather than ammonium nitrate, because it is much more nitrogen per unit of mass than the ammonium nitrate. Okay, now a couple other terms in here. Sometimes we might be asked to calculate what's called the percent by mass composition. Percent by mass composition. Now, if you're asked to calculate the percent by mass composition, we are not specifying a specific element, but rather you would calculate the percentage for all of the elements that are contained in the compound. So in the case of ammonia over here, if we wanted to find the percent by mass composition, we'd find the percentage of nitrogen and we'd find the percentage of hydrogen. And so to find the percentage of hydrogen, one of the ways we could find the percentage of hydrogen would simply be to do the same thing, that is take the part, divide it by the whole, multiply by 100. So we could take the 3.024, divide it by the 17.03, and then multiply by 100. Or, what would be another way we could arrive at this answer?
Subtract 100.
Subtract from 100, exactly. Because the percentages should sum to be 100%. So if we took 100.00 and subtracted from it the 82.27, we would wind up with 17.73% hydrogen. So again, the percentages should always sum up to be 100%. And so that would be done if you were asked to calculate the percent by mass composition, and no element is specified. Now here's another lesson. Again, this would apply if you're using fertilizers of some sort. Now you yourself may not be a homeowner at this moment, but at some point you probably will be. And when you do, you may be taking care of your lawn and such. If you were to wind up purchasing fertilizer, you would go into the store and you're going to see some numbers that are written on the bags. For example, you might see a number written like this as 10, 10, 10. You might see something like 27, 5, 12. And those numbers are going to appear on the container of fertilizer that you buy. Now these numbers have a meaning. Any idea what the meaning of these are, or anybody know?
It's a concentration.
What is it? Yeah, percentage of elements. Now, do you know which elements they are? Okay, one element, though, we should know already, and that would be? Nitrogen, exactly. In fact, the first one here is nitrogen. Any other idea of nutrients that are important to growing things?
You said urea.
Now, urea, I should actually say elements. Phosphorus is one, exactly. And that's the middle number. And then the last one is K. These are called NPK values. NPK values. And they represent respectively the percentages of nitrogen, phosphorus, and potassium that's contained in that fertilizer. Now, sometimes there's a fourth number on there. And if there's a fourth number that's on there, that number is usually pretty small. It might be like a 2 or a 1 or something. And if the fourth one is on there, then it's an S. So it's an NPKS value. And of course, S would be sulfur. But again, most of them is just simply the NPK values. Now, as far as what they're used for, N, nitrogen, is used to make things green. If you want a green lawn, you want a big number for the first one. So the first one is the stuff that's going to give you the beautiful chlorophylls and everything, the bright green. P is used for fruiting and flowers. So if you want something to generate large fruits or large flowers, then you want a large P value. And then if you want healthy roots, then you want a larger K value. In fact, now there's some ways you can kind of keep some of this together. For example, can you think of a root crop that kind of sounds like this element? What is it? Potato, exactly, potatoes. Potatoes contain the element potassium. Okay, potatoes contain potassium, high amounts of potassium. So that would be one way to keep this one straight over here. Now in the state of Minnesota, if you apply a fertilizer to your lawn, by law, one of these numbers here has to be equal to 0. By law, if you put it on your lawn, one of these values has to be equal to 0. Any idea which one we want it to be 0? Phosphorus, exactly. In Minnesota, the P value, the one of phosphorus in lawn fertilizers, must be equal to 0. And why do you think we want? Remember what the potassium, the phosphorus does. It causes things with fruit and flower. Yeah, grass. But why would we not want that in there?
Because it's Minnesota. Don't we have a drier soil?
Grass.
You actually want grass that's going to flower and seed and everything.
It's the type of soil that's in this climate.
Well, where do you think fertilizer often winds up?
Lakes.
Lakes. Yeah. Because out in lakes, what's going to happen out in lakes? Algae, exactly. So you've probably heard of algae blooms. Okay? So the algae blooms are caused by large amounts of phosphorus contained in fertilizers. So what will happen, and this is why you'll hear about the DNR or whatever, discouraging property owners now. If you own a lake property or your parents do or know somebody that does, they don't want you mowing right up to the lake. Okay? Because there has to be some buffer that prevents the fertilizers from running in there. Likewise, when you apply it to your lawns, you don't want to apply it right before a big storm is forecast. You might want the rain to come down, but if there's a big storm that's forecast, then it's more likely that that fertilizer is going to just get washed right into the storm sewers. And so if you go out in the roads, you'll see the storm sewers are the things that are right along the curbs there. You know where the storm sewers drain to? Lakes and rivers, exactly. So they'll drain out of there, they'll run right into the lakes and rivers, and then that fertilizer gets in there. And then if it's really rich in phosphorus, then that's when you see the really green lakes, green ponds, and whatever else. Now, of course, when I was growing up, every farmer had like their own pond out in the fields. that the cows would drink from, but it turns out that there's something else that's really high in phosphorus, and that is, and here's an easy way to keep it straight, P contains P. Okay? P contains P. Urine, P, contains large amounts of phosphorus. So what happened then is that these cattle would go ahead and urinate a whole lot by their drinking source. And one of the reasons why if you go out by the farms there, you see the super, super green ponds and everything is because that urine contains large amounts of phosphorus, and that encourages those algae blooms. Now, one of the things you probably haven't heard of, I mean, we've all heard about an energy crisis, however you want to define it, global warming and such, coming from the fact that we are taking out of the ground things that have been locked in the ground for millions of years, our oil and coal and such, and when we burn it. But the other thing that's been locked in the ground for a long time is phosphorus. And so when plants and animals die, what will happen is that over time they decompose, they get compressed and whatever else, and they turn into oil and coal. But the other thing that happens is that your bodies, animals, our bones, the primary component of our bones is calcium phosphate. So what will happen then is that as animals die, all that phosphorus and stuff in our bones will begin decomposing. As it decomposes then, you wind up with rich concentrations of phosphorus. And it's called phosphate rock. And in fact, when we make fertilizers, very often we don't have ready supplies of phosphorus. So we go ahead and mine phosphate rock to generate the phosphorus in our fertilizers. Well, now there's a finite supply of phosphorus locked up into these phosphate rocks, just like there's a finite supply of oil and coal that's available. So you've heard only about the problem of oil and coal right now, things we get out of the ground, these fossil fuels. Again, what you probably haven't heard of is the phosphate rock. Now, if you think we have fights in big controversies here, politics or whatever, about oil and coal right now, just wait till we start hearing about controversies associated with phosphorus. It is going to be an issue. It's not going to be an issue that's going to be dealt with in our lifetime. There's a lot more phosphate rock that's out there and available than there is oil and coal. We might have 500 year supply of phosphorus available. Okay, so it's not going to be our immediate generations, but at some point, phosphorus is going to be a big issue, assuming we still have human civilization around here in the future. So, what may start happening if we start addressing these things in the future at some point is that because P contains a large amount of P, at some point in the future we will probably be collecting all of our P, all of the urine and everything, to try to mine the phosphorus out of there as a supply for the phosphorus in our food chain. So it's kind of an interesting circle here when you think about things, but we can't keep consuming things and dumping them out in the lakes and rivers or whatever else and expect that there's going to be an infinite supply of things, because there's not. So again, phosphorus is kind of one of those interesting things that again, probably our descendants at some point will be dealing with. So with that, if we were to do a NPK value for ammonium phosphate, not ammonium phosphate, ammonium nitrate, what would the NPK value look like for this stuff? Well, what is the percentage of nitrogen?
35%.
35. What is the percentage of phosphorus in there? Zero. What is the percentage of potassium in there? Zero. So the NPK values for ammonium phosphate would be 3500. Okay. So any questions? All right. Then let's see. Here's another use for these percentages. Might be if we were trying to, instead of putting stuff out in the field, maybe we wanted to take something as a supplement. So lots of times pregnant women need extra iron in their diet, so they are prescribed an iron supplement. Okay, so an iron supplement contains 25.0 grams of this stuff. And I think I heard somebody say it. Ferrous sulfate, exactly. That's the old name. The old name is ferrous sulfate. Today we would call this one iron 2 sulfate. But again, in the medications, they still call it ferrous sulfate. And we'd like to know, what is the mass of iron in the sample? Okay, what is the mass of iron in the sample? So now to do this, we are going to go ahead and calculate a molar mass once again, but we're going to write them all out. And you'll see there's a purpose for us writing them all out. How many irons are in this formula? How many irons are in here? One. How many sulfurs are in here? And how many oxygens? Okay, so then we're going to multiply these each by their atomic masses. We already found oxygen is 16.00. We come back and look up sulfur. And we see that sulfur sits here at 32.07. And there's one of them. And then we have one iron. That iron sits at a value of 55.85. So we'll multiply each of these through. We'll have 1 times 55.85, which is 55.85. 1 times 32.07, which is 32.07. And 4 times 16, which is 64. And of course 64.00 considering significant figures. We then sum these together. We get a 2, 9. That's going to be a 1, 5, 1. Now here's kind of an interesting thing. First of all, let's go ahead the way that we learned this already. We said that this represents 1 mole of FeSO4. And 1 mole of FeSO4 equals 151.92 grams of FeSO4. This would be the grams of iron, grams of sulfur, and grams of oxygen. Again, we see how they all sum up here. And I said this wrong because that would be one hella big pill. That's not a gram pill. That is going to be a milligram pill. So if you were missing it, yeah, we don't want to take a 25-gram pill. You're going to be gagging on that one for sure. All right? So we want a 25.0 milligram pill. All right. Now, and I would never want to be pregnant, by the way. So I empathize, sympathize, whatever you want to say. So now, if we want to simplify this problem, if this is given in milligrams up here, and this here is in grams, one way we can do it is we can convert this here to grams first, or here's another way. What I'm going to do here is I'm going to say it'd be a lot easier if we could put this in units of milligrams. And it turns out that if we take this number here by 1/1000th and get 151.92 milligrams of FeSO4, then we could also multiply this number by 1/1000th, and this would be a millimole. So we're actually dividing each one of these values by 1,000. We're actually not dividing the numbers by 1,000, but we're dividing the units by 1,000. So it turns out that 1 millimole of iron 2 sulfate is equal to 151.92 milligrams of iron 2 sulfate. Which of course means that these units here would be all represented in units of milligrams. Now here's the beauty of these calculations if you set it up like this. These mass ratios would always be the same. For example, if we weren't dealing with milligrams, we could, if we want, put these all in units of kilograms if we had wanted. And of course, if these were kilograms, this would not be a millimole, this would be a kilomole. Now, we could also deal with these in pounds if we wanted to. So this would be pounds, 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 pounds. This is no longer anything that we could put down as a value, but these ratios would still hold true. These mass ratios, regardless of which unit we use, those mass ratios would always remain the same. So what we're going to do though is we're going to calculate this in terms of millimoles, because we are given this value in units of milligrams. And that's going to make our work a lot easier on this. And so as you do these problems, you're going to see some given in different units. You might see them in kilograms or whatever. Just remember that these ratios stay the same in terms of the numeric values. So now if we wanted to go ahead and do this problem, we'd start off with what we're given. In this case, we are given 25.0 milligrams of FeSO4. And what is it we're looking for in this problem?
Mole.
We're looking for the
Oh, the
mass of the iron.
So you want 1.
Now, which unit do you think we'd probably give for the mass on this one? Milligrams, exactly. If we're given milligrams, the most common sense unit to calculate is going to be milligrams as well. So now, if we want to get to that answer, all we need to do is to find a ratio between these two substances. And we have that ratio right here. So place it in to get those units to cancel. On the bottom we'd put in 151.92 milligrams of FeSO4. On the top we'd put in 55.85 milligrams of iron. At this point, the milligrams are going to cancel out. And then we'll go ahead and calculate this. We'll take 25, multiply it by 55.85, and we'll divide it by 151.92. Now once we get this answer, we should round it off with the correct number of significant figures. So this would be written as 9.19 milligrams of iron. Of course, now once you calculate that, you should ask yourself if this answer makes sense. Should this number be bigger or smaller than the mass of the tablet itself?
Smaller.
Smaller, exactly. If the iron is contained in the tablet, it has to have a mass that's smaller than the amount in the tablet altogether. Any questions with that one? All right. Last thing we're going to do. This one here is just to get us to play with the units a little bit more. Let's say we're dealing with the number or the substance C2H6, which is called ethane. And we had 1 molecule of ethane. 1 molecule, and this is something we've already covered. We didn't quite put it this way in terms of calculations though. How many atoms of carbon would there be in 1 molecule? 2. How many atoms of hydrogen would there be? 6. Quite simple. So now let's say that we had Avogadro's number of molecules of C2H6. How many moles would there be of carbon?
6.
How many moles would there be? 2. How many moles of hydrogen would there be? 6. Exactly. So if 1 molecule contains this many atoms of each one of these, we multiply by Avogadro's number. We multiply each one of these by Avogadro's number. And so multiplying them by Avogadro's number, we have the units of moles. So they retain the same. So if we then said, how many moles of carbon are in, let's say we have 12.7 moles of C2H6, we could then use this as a conversion. And using it as a conversion, we would say we have 12.7 moles of C2H6, which is what we're given. We're looking for moles of carbon out here in the answer. We then need a conversion that will get our units to cancel out and give us the ones we desire. So for this one here, we look at moles of which stuff on the bottom? C2H6 goes on the bottom, and on the top would put in moles of C. The number that goes on the bottom would be how much? 1. And the number that goes on the top is going to be 2. It's that simple. It's a molar ratio. So these are going to cancel out. We'll take the 12.7, multiply it by 2. When we do that, we wind up with a result of 25.4 moles of carbon. So now you try this. Let's take 7.6 moles of C2H6. And we'd like to know how many moles of hydrogen are in the 7.6 moles of C2H6. And once you get that result, you'll pop it into the Socrative app. How many moles of hydrogen are in 7.6 moles of C2H6? Okay, we'll give you about 15 seconds to lock in an answer. And we'll count down 5, 4, 3, 2, 1. And the correct answer should be 46. Because how many significant figures should there be? Just 2. So it's 46 there for the answer. All right, we are going to work on some problems here for the rest of the hour. Before we do, I have a couple of questions for you. First of all, anybody know what these are? Well, more specifically, how come I can't do this? How do I do this? I'm not used to using my pointer for this. How do I do this? Is this it? There we go. It's 3 moles. Huh? How about that? Do you know what this is? Molasses. All right. So now I don't know how to get out of here. How do you get out of here? Keep? No, we'll discard that. There we go. So here's what you need to work on here the rest of the hour today. In your textbook, in chapter 6, 5 problems. Number 63, letter C. Number 67, letter A. Number 77, number 83, and number 113. These are all odd number problems. They have answers in the back of your book. If you didn't bring your book with, I know that most of you are equipped with your cameras. I happen to have written these problems down below here. They'll scroll off the screen. Or you can work with somebody that has the answers in the back of their book. There's 63 and 67. Okay, and then I'll go down for the last three. Here's 77, 85, and 113. But now, you'll see a few people that have their books with today. If you have your e-books, remember you can get your e-books accessed through either Mastering Chemistry or etext.pearson.com.